I think that the organizers, if they feel ready, they can already start. So, I mean, perhaps me and Professor Tandini can say a couple of words as introductory. I mean,
no. I mean, this is, I'm very happy. I'm very happy, and the program looks very nice, and I like very much the mix and the mix of contributors from different groups. This is a big success for me, at least. So I leave the floor to the organizers who did all the work, basically.
So, organizers, feel free.
Okay, let's start. So welcome to this workshop. First of all, thank you everyone for being here. So this event was conceived as an opportunity for a younger researcher coming from different backgrounds to meet, show their research activities, and open a dialogue about their research goals, and also about how this can be achieved by leveraging on a multidisciplinary approach. So probably in the research experience of everyone here, whether the primary objective of your research is to understand the human mind or to build new technologies or robots and with a sort of intelligence, it has always been necessary to exploit the knowledge gained in both the field of cognitive and computational sciences. So in this prospect, it is important that the two areas continually exchange their views, their ideas, and also find a common dictionary.
So to give you an example from real life, while organizing this workshop, we found ourselves comparing the different meaning each one of us was giving to the word interaction, depending on our different backgrounds. Thus, we decided to organize this event as an occasion to make both robotic system psychologists sharing ideas and their own research, and maybe find also, external collaborations with colleagues that might come from a different background. So the workshop will be structured in two main sessions. The first one will include the presentations from Marta Lorenzini, Enrico Valli, and Maria Lombardi, moderated by Sesco Vilenze. The second session will include the presentation from Dalila Albergo, Noemi Montobbio, Daniele Esposito, and Marco Emanuele, moderated by Fabio Vannucci. Each session will be followed by a roundtable discussion in which you can address the questions to the presenters. And after the two roundtables, we will have a general open discussion about the topics we have addressed. So please stay with us until the end because we are sure that you will like the interesting discussion that will come out from this event. We hope, at least. Now a brief reminder about how to ask questions. You can use the Zoom chat, asking directly the questions to the presenters or raising your hand and take the floor. Otherwise, you can use the Padlet platform and write your questions below the column corresponding to that specific speaker. And then we will ask the questions for you to the speaker. So,
yeah, you can see now on the screen, I'm sharing the Padlet homepage. So you can just, as Serena said, post there your question under the column dedicated to each speaker. And then we have also one for the final open discussion.
Okay, so to break the ice, maybe now we can kindly ask you to answer some questions just to understand which is your background and, make everybody know a little bit better each other. And we prepare some questions via Mentimer platform that Lynn already shared. Cool. And
you can find
you can find the
link on the Zoom chat.
Cool, already. So maybe Linda can guide you through the Mentimer.
Yes, you can go on menti.com and you can insert the code you will see at the top of the page, 42835313. And when you start answering, we should see the outcomes of here on the page. So, okay, someone is coming. Let's take a few minutes to answer this. Okay, so almost 30 already replied. We're quite balanced.
A lot of engineers.
Yeah.
I was about to say, I think engineering is winning.
Yeah. Okay. So maybe just one more minute.
Curious about the triada.
Yeah, definitely.
Write it in the chat or on Padlet.
Yes, please share with us your background for the three ones for the other.
Okay.
Okay. Okay, so a lot of engineering and roboticists, but also quite a bit of cognitive science, neuroscience, and so on. So nice. And we also prepare another question for you. That is, in your research experience, do you collaborate with colleagues with a different background? So the code should be the same for answer it. And then let's see. Okay.
I love this tool. It's great.
So we can say that most of us do, but someone not. At least there is the will to work collaborate. But
yes. This is the spirit of this workshop.
Yeah, but feel free to answer no, there is no need. So
we won't judge you.
Okay, so thank you. And in any case, you can also answer during the workshop. I think it's fine. Okay. And okay, now how can I? Okay. And we have actually other two questions, so it's always to answer on Menti. Giulia will share the code in the chat, and I will share the screen again. So there are a bit more general. You have multiple options you can insert. So what comes to your mind when you think of cognitive science? So use your fantasy. And the code is 13325178. Okay, they're starting to come.
I think about.
Wow, very nice.
This is essentially the academic version of the Eurovision voting.
Yes, interesting.
A lot of interesting prompt from discussion here.
Yeah.
I'm trying to find if there is action, but perception is very, very noticeable to most people, whereas action is not on the same.
There is also cool, that is nice.
Also a lot of human keywords like human like, exactly.
Okay. And of course, we have the same question, but with robotics. So it's the same. What comes to your mind when you think of robotics?
So already to control. iCog, of course.
Future is common. The both of them.
We all agree. We all agree about the importance of both fields in our future.
Well,
That's great.
And human likeness, humanoid, human-robot interaction.
Okay, there is also a body that was not trivial.
Movement.
Yes. Help.
It's anthropomorphic. It's there.
Okay. So of course we will come back to this answer also later in the general discussion that will be after the 2 sessions of presentations and roundtable.
Yeah, I think we can now proceed and
and then if you want to add your answers also later, let us know and I will activate again Menti. Okay, thank you.
So intelligence is the center. Both one was intelligence, the other was artificial intelligence, but that's
Yes.
Nice.
Very nice.
Yeah.
Okay. So we would ask also for the last one, the
interaction.
The interaction.
Okay. So there is a very last one that, as Serena said before, came to our mind when we were preparing the workshop. So we discovered that we have quite a different understanding of the word interaction. So we're asking you, what meaning do you give to the word interaction? And the code, Giulia shared it, is, I will share the screen as well, 18458583.
Okay, so take your time also to answer to this last question, but in the meanwhile, I think we can proceed with the first session of speakers. And then we will come back to these answers later. So I leave the floor to Sesco, right? The first moderator of the first session.
Okay, so I will stop sharing, but you can keep answering on Menti as well.
I have not much to say except I think we need to get a move on. So just to get started on the first speaker. That is Marta.
Good afternoon to everyone. Can you hear me?
Yes.
Okay, I'm going to share my screen. So first of all, thank you for inviting us in this nice event. Can you see my screen?
Yes.
Okay. Here we go. So, good afternoon to everyone. I am Marta Lorenzini from the Human Robot Interfaces and Physical Interaction Lab at IIT, whose head is Dr. Arash Arjudani. Today I'm going to present you my work about human-robot collaboration for the improvement of workers' ergonomics and productivity. So let's consider the current industrial scenario. We have the work-related musculoskeletal disorder, which have a high impact on the worker health and quality of life, and but also substantial cost, economical cost for companies. Then we have the mass customization requirements of the current market that is forcing mostly the small and medium enterprises to go for more flexible production processes in order to avoid outsourcing. And finally, we have the workforce that is getting older year after year. Our idea is that a concrete solution to all these issues can be offered by collaborative robots that can offer their support, their physical support to the workers, but also improve the flexibility and the reconfigurability of the production processes. So the idea is that in the past, the robot in the industrial scenario were limited into cages, and basically their job in terms of safety for the human was to avoid collision with the human. But now a new generation of robot is developing that include direct and physical interaction with the human in order to solve all the issues that I've mentioned before. These are the pillars of the HRI2 lab. Let's start with human ergonomics. So if you think about the worker in the industrial scenario, every day they need to perform repetitive and heavy manufacturing tasks. That since they perform every day for hours, they can lead to injuries and chronic pain. So our idea here is that we want to monitor the load of the worker while performing this kind of repetitive and heavy task in order to provide them with a feedback about this load, but also to guide them and to help them to avoid excessive overloading, but also to adopt improper posture. The starting point in this direction is first to monitor this physical load of the worker that they are performing this kind of task. And in order to monitor this load, we need to use some sensor system. So for example, here in the video on the right, you can see that the subject is standing on a force platform that in order to monitor the forces that the human exchange with the ground, but also an XM suit that is an inertial based motion capture suit in order to monitor the kinematic of the human. So the idea here was to firstly identify the contact point of the external load that was applied on the human, that in this case is the weight of the box. And then once the external load, the contact point of the external load is identified, it is possible to understand the overloading that this external load is imposing on the human joints. And through an intuitive feedback interface, it's possible to understand if this load is risky or not. So there are some spheres that are color coded in order to provide information about a red, so a high risk, or a green that is not high risk, in order to convey the information about how ergonomic is the body posture. At this point, we have the role of the collaborative robot. So after it is possible to estimate the physical load that is induced on the human by an external object, it's possible to understand which is the body configuration that is more ergonomic. So the robot move and guide the human toward this more ergonomic configuration, that is the one that minimizes the overloading imposed on the joint by the external load. Then the system is intelligent, so all the time the robot can move in order to follow the movement of the subject that is changing the hand or moving into the workspace, because all the time there is a camera that you can see on the top right that is able to understand the configuration of the human, but also the position of the human in the environment. The next step is to pass from a fixed robot to a mobile robot. So here you can see a robotic platform which a robotic arm on the top, and the robot is moving toward the human he needs to collaborate with, and for performing the first task, that is in this case is an handover task. The robot is able to understand which are the parameter of a particular subject, because the algorithm is subject specific, to understand which is the more ergonomic posture in order to perform the task for a specific human. Then the robot can move toward the second subject that again is wearing the suit in order to understand the person kinematics and to perform the ergonomic task for the specific task that is a drilling task with the specific subject specific parameter of the second subject. After this, the further step is to place the robot in an environment that is not empty, because an empty environment is not realistic for an industrial scenario. So we combine the ergonomic framework with a navigation system for which the robot can move in an environment in which there are both fixed obstacles, but also moving obstacles that can be for example, another human that is moving in the environment, that is the coexisting human. So the robot is able to distinguish between the coexisting human and the collaborative partner, that is the target of the navigation. And once the position of the collaborative partner is found, the robot is able to perform the ergonomic task with the subject-specific parameter of that particular subject, and to find the body configuration that is the more ergonomic in order to perform the task. And this is the idea of the work that we are doing in terms of human ergonomics. Another topic I want to share with you is the shared effort allocation between human and robot during human-robot collaboration. So here you can see, for example, collaborative task between a human and a robot. It's an assembly task in which the task assignment is obtained according to the kinodynamic characteristic of the two agents and of their skills. In this case, simply the robot is performing the tasks that are not possible for the human, because he needs to take some pieces that are in a workstation that is too far for the human. While the human is doing the task that is the subtask of the task that are more precise and more complex and too difficult for the robot. So basically they are combining the physical skills of the robot and the cognitive skills of the human in order to perform together the assembly task. So in order, all the time the human is provided with an augmented reality interface in order to have to be more aware about the assembly task, and it's possible with some indication that are in the augmented reality to understand if the robot is approaching the human, or if the robot is far from the human, so in a safe place. So depending on the color of the light, the human can understand, and also if some gestures are needed in order to make the robot, for example, leave the pieces or move in a different way. And in this way, they perform the collaborative task together. This is another example in which the human and the robot need to take some boxes and put them on a pallet jack. So first, there is the online estimation of the position of the boxes and the pallet. Then there is an algorithm that, depending on the weight and size of the boxes, that can be found thanks to some labels that are put on the boxes themselves, to understand which box is too heavy for the human, so the robot can take it and put it on the pallet. Then the human can take the smaller box that is a less demanding job in order to perform the task. And while the robot is performing his job, the human can do some other things. But when the box, for example, is too big for the robot and also for the human, they can do the task, the collaborative task together. So put the box in the optimal position. Also, an optimal optimization algorithm was associated in this work in order to find which was the best positioning of the boxes into the pallet. And the robot was provided with both a locomotion and manipulation control in order to perform the task. And this was another example of the shared allocation algorithm that we are trying to implement. The last thing I want to share with you is about the investigation of the cognitive load, because so far we have focused on the monitoring on the physical load of the worker that they are performing their job, but we would like also to develop some indexes in order to understand which is the cognitive load of some task, like the assembly task or some collaborative task with the robot, in order to first provide the feedback to the human about which is the cognitive load associated with his or her activities, but also for some other task, for example, task allocation, or for the improvement of human-robot collaboration. So this is all from my side. Thank you for the attention, and if you have any question, I would be happy to answer.
Cool, thank you. Just before while we transition to the next speaker, just a timely reminder that we'll save the questions till the end of this session. Please ask them in chat, or at the end, just raise your hand or use the Padlet app. We're now moving to Enrico, who's also working on collaboration, but more like the robot perception of the human, if I understood correctly. So Enrico, it's over to you at this moment.
Exactly. Good afternoon, everyone. I hope you can hear me well and see me well as well. So try to share the screen. Okay, now you should be able to see the presentation.
Yep, we see it.
Perfect.
All yours.
Okay, perfect, good. So thank you very much for being here, first of all, for allow us to be here. And what I'm going to show you today is our project iFeel, which is meant, let's say, to create a wearable technology for agent-robot collaboration. So yeah, something very similar to what we saw just now. Okay, so first of all, before starting is who we are and what we do. So we are the Dynamic Interaction Control Lab of IIT, and we mainly work on three different research axes. The first one is the aerial humanoid robotics, in which we are working on make our robot iCog flying. So this, why this? Because we would like also to give a different means of transport to iCog in order to respond to disasters like fires or earthquake on places that we cannot reach easily walking. Another idea is also to deliver heavy payload in general. The second research axis we are working on is the teleexistence. So we basically work on make a person existing in a remote different environment. This, of course, enables the telepresence and improve also the augmented reality. The last axis we are working on is the agent-robot collaboration. This is more related to the presentation that I'm showing you now. So in this, let's say in this frame, we are trying to make robot and human collaborate together. And we started since already 3 years ago, almost, with a project, an European project called ANDI, is an H2020 project. We started developing algorithms, artificial intelligence algorithms that are capable to make human and robots working together. So why this? The main reason is that there is an increase in demand for collaborative between human and robots. This especially in the industry, if you think about what we just heard from the previous presentation about the musculoskeletal disorders. So there are problems that workers can get during the daily activities in case they have to carry on heavy tasks or do difficult duties. What is the main problem, the main challenge that we have to face for that is basically the fact that the human movements are not predictable when they are working together with a robot. So we need to give the robot the capability to perceive the human movements and also to perceive the human environment and what the human is doing, so the fatigue that the human is doing during the task. At the same time, we need to do also, we have to give the robot the perception of the human. So it is something that has to be done in both sides. So to solve this problem, we decided to create a closed loop system. We started basically from modeling the human as a rigid multi-body system. Then we added sensors to the human body in order to get inertial data, so the movement data from the person, and also dynamic data through sensor that we use in the shoes for force and torque that we are exchanging with the ground. We decided then to send also this information real time to artificial intelligence algorithms that are capable to estimate the motion and also the dynamic of the body during the task. Out of this algorithm, we are capable to get some analysis, to create some statistics analysis, and then to drive the robots in order to allow the robot to help the person during the task in the best possible way. On top of that, since also the other pipeline is very important, so to give feedback to the human, we implemented other algorithm of artificial intelligence in order to give the feedback. In the special situation now, we have multi-haptic feedbacks that we will see later. We give real-time feedback to give a perception to the human of what the robot is doing. So how did we do this? We mainly create wearable systems. So what you have just seen in the previous presentation with Xsense, we are trying to, we are working on replicating what Xsense is doing, and we are adding the possibility to add different type of sensors. So not only related to the inertial, so to the movement of the person, but also to the psychology of the person. So adding, for instance, biometric data. So we have, as you can see here in the left figure, we have some nodes. The small one that you see here is, I hope you see my mouse. You see small nodes that they are more or less the size of 50 millimeters times 30 times 15, just to give a rough idea. We add these sensors to a suit that we created, and then we use also these shoes to understand, let's say, the forces and the torques that we are exchanging with the ground. So without the need of force platforms that allow you to do all these tests, but only in a certain position. With this, we are, let's say, able to move wherever we want. So here in the right side, you see let's say the overview of the communication. So you see a network, which is a wireless network that we created ourselves. We send real-time information to a central unit, to a normal PC that is running the algorithm for the estimation. Then we send we process the information real time, and we send the due information to the robot. In the pipeline, the back pipeline, we send, for the moment, haptic feedback to the human, but we are planning now, we are working on actually, to give feedbacks in terms of also of temperature and other type of feedback that helps the human to perceive the robots and the environment in which it's working. So this is an overview of the algorithm that we are using. So basically, we developed in the previous years the motion tracking with an IK, so an inverse kinematic algorithm. We also developed a whole body human joint torque estimation and a multi-human real-time visualization of motion and joint effort. This you see the structure of this. So basically we have some devices, the one that I showed you before. So the motion tracking suit, sensing shoes, robot, and any other device that they are connected together in a network with some remapper interfaces. we have the human model that we created ourselves, and then inside we have this algorithm for the human kinematic, take data from the movement of the people. We combine this with the human forces provided by the shoes that I showed before, and then we put it together. We get the estimation of the articular stress of the person. The picture in the right shows you the visualization using the ROS, but everything is can be done also using YARP. So, okay, this is a typical example, is in an industrial scenario. So here you can see using, this is an old video, I think was done almost a couple of years ago. So here we were using Xsense, so it's a commercial off-the-shelf system for the kinematic acquisition. And then you see here that during normal, say, typical scenario in a warehouse, for instance, where people are carrying on loads, there is an exchange of load, and here you see with different colors the stress analysis of the joints of the model of the human, and you see also with the arrows the external forces that are acting to the person. A second. Okay, this is another, scenario, which is more medical and rehabilitation, which you see shoes that still are the old version of the shoes, still with wired and with the force and torque sensors. And you see here the estimation, the gait analysis is also the estimation of the forces on the body and the fatigue analysis of the joints of the person. Then I would like to show you a validation of the technology that I was telling you before, so the iFeed, the hardware itself. And as a first validation in the lab, we decided to do a retargeting, but this is not, of course, the only thing that we can do. So the target is only the first validation of this, technology. And here you see a person wearing the suit with the upper body retargeting. So the robot is copying exactly in real time what the human is doing. Then, of course, next step is to give, let's say, appropriate information to the robot in order to help the robot to help us during the tasks. Okay, this is one side, so one direction. So the direction is from the human to the robot. And then we have also the other direction, which is from the robot to the human. And we did the first test of the validation, let's say, of the multi-haptic system. So basically here you see that touching the robot, we have system in the right hand of the colleague of mine that is a vibration actuator with some LEDs just to show for the video, but there are vibration actuators that they are vibrating, not only with a normal vibration, but with a haptic vibration. So there is a possibility also to change the frequency and the type of the feedback you want to give, depending on the touch, how much you touch the robot. What we are doing at the moment is to increase the granularity of this in order to be able to understand exactly in which part of the robot we touch. Okay, so all this project is leading to an idea of spin-off. So we are planning now to create a spin-off out of this idea. So here you see there is a website already in place. You can visit and you can follow us to see the next, let's say, the evolution of this project. And we also started with a LinkedIn page. So I concluded the presentation. If you have any questions, then I think we go on later to the Q&A.
Cool, very interesting, and best of luck with the spin-off, with the startup.
Thank you very much.
And also the shoes look really trendy, so I will try to find a pair. Let's move to Maria, the last speaker of today, and then hopefully we'll have a few minutes left to answer some questions. There are a lot of questions coming in, so that's cool. Maria, over to you.
Yes, I'm here.
Enrico, you will have to stop sharing.
Enrico, I think you need to stop.
Yeah, exactly.
Sorry, now it should be fine, right?
Yeah, we can see your presentation. Yeah. It's all yours.
Okay, can you see the screen, I think?
Yep,
Yes.
we can see it.
Okay. Basically, I'm Ria Lombardi, and I'm working in Humanoid Sensing and Perception group. And basically, as you can see also from the title and from the picture, my project is basically on the gaze estimation in human-robot interaction. So I'll describe a bit the overview of the work, and then the learning strategies that we use to address this problem. As a humanoid sensing group, basically our aim is to endow basically the robot, and in particular iCog and R1 we need several skills. For example, the navigation, the grasping, object detection, but in the framework of iCog, I'll focus more on the gaze estimation, and in particular the gaze as a social cue. Basically, the gaze estimation is the process aimed at identifying the observer point of regards, and the gaze basically is an important non-verbal social cue, because it has been proved that can enhance memory and can influence the human attention, or in general human behavior. From a robotics point of view, this is a new step. Basically, we are adding a new feature towards a robot, basically in the context of the social robotics, where the robot is required to interact naturally with a human, and so also follow a set of social behavior. And instead, from a scientific point of view, basically is of interest to understand if the human has the same cognitive response or reaction in the interaction with the human, and during the interaction with a robot. The aim of the project basically is to design a module for iCog able to understand where the partner is looking at in real time in a frontal joint task. And in particular, we want to understand from iCog's camera if the partner is establishing mutual gaze with the robot, or if it is she is looking at on the table elsewhere, and also if the user is looking at in general at iCog's body. Here the challenge is that we rely only on the iCog's camera without any external equipment like glasses or eye tracker. And as you can see, the quality of the iCog camera is very, very poor. This is the typical work plan that we have in computer vision or in general in the learning strategies. We have the collection of the data set, because the learning needs a lot of data to train its model. And then we have a demo, in general, the validation. To collect the data set, basically we ask participants to look at in several points in the space, and the target point basically is marked with an Aruko marker. So if we have an Aruko marker in the space, we can reconstruct the coordinates X, Y, and Z of that at the point in the basically in the robot coordinate system. The second step, having the data set, the second step is to train a learning architecture. So we have for each human frame in frame picture, we basically detect the face point of the human through open pose. This feature vector basically is used as input in our architecture, where we have a first layer of a mutual eye contact classifier. If the result of this classifier is yes, basically we understand that the human has an eye contact with the robot. If no, we have another layer, and in this second layer, a regressor that basically estimates the x and the y of the gaze the direction of the human. This is a project still under working. So this first part of the mutual eye contact classifier has already done, and we are going on basically with the second part. Just to show you that this work, basically on the right, we have the output of the open pose, where we detect the points of the body and of the face. On the left, we have the output of the classifier that can detect if the human has established a mutual contact with the robot, and C here is the confidence level of the classifier, and basically is quite robust also to the movement of the head and of the torso. Okay, so basically this is just an overview of only the gaze as a social cue, or out of all the other tasks. And basically the next step is going on with the gaze estimation in the general, and also perform also experiment in a real scenario together with the as for HR group. Wait, thank you for your attention.
Cool, thank you. We have some time for questions left. A few came in on the Padlet. What I would suggest is, because we won't get around to all of them, but the Padlet questions stay. So I would like to invite the speakers to answer the ones that we didn't get around to afterwards. And also, I don't think we'll get around to much overall colloquial discussion, but we can always use the roundtable discussion at the end of today for that. So I'll just pick a few questions at random. Questions for Maria are still coming in. So I'll just relay a question from Fabio to the first speaker. Let's go in order. Whether you thought about adding certain human features to the robot, such as a face or voice, things like that, and whether you think that would have an effect.
Okay, thank you for this question. So we never thought, at least for what concern our work, we never thought of adding a face or some human feature to our robot, because in our view, the robot is just a smart tool for the worker. So it doesn't need to be a physical assistant, a human assistant for the worker. It's just a tool as a I don't know, a driller or a hammer can be, but is an intelligent tool. So we don't want the human to see the robot as another person collaborating with him, but as a, again, as a smart object that can use for his for completing his task.
Okay, thank you, Fabio. Fabio?
Thank you for.
Okay, we have questions for the other speakers too. So let's
Okay, sorry for the echo, but we still have to coordinate with the microphones. Yeah, thanks for the answer.
Yeah, cool.
Enrico, somebody asked if you could give us some possible applications of retargeting in scenarios of human-human interaction or even social human-robot interaction. If that question needs to be clarified, you can type in chat, whoever asked that.
Yeah, I think, I mean, I can give some example of human-robot targeting. Then human-human is not exactly clear to me what it means. So the retargeting human-human, so is using, let's say, two suit to different humans and give a feedback, or is something different? Because I don't see a real, let's say, idea behind having two humans help each other, because I mean, they can help each other, but then to give feedback to one to the other, I think we can simply talk unless there are problems, different problems. But if some clarification probably are needed to answer properly to this question.
Yeah, this person is marked as anonymous because Padlet does that, but yeah, feel free to clarify question so Enrico can answer that. That's question for Maria also came in. Maria, how did you get the ground truth of the gaze, which was used to train your model?
Yeah, basically, as I said, I use Arupo markers to get the ground truth. Basically, the Arupo markers are just a pattern of squares that can be black or white. And if we have this Arupo marker in the space, in the 3D space, we can algorithmically from the picture of the marker, we can get the position of that marker, and so the X, Y, and the Z in the robot coordinate system. So from the robotics point of view, from the robot point of view, we know where the user is looking at, if basically the user is really looking at that specific marker.
Oh, we talked about the interaction before, but there's no way to know if the question has been like satisfied. But for me, it has really cleared things up. Giulia, did you want to ask your question to Marta just in person here?
Anyway, Marta has already answered to my question, partially answered to my question by answering to the question of Fabio, because I was curious to know whether they have thought to give an agency to the cobots, to the robot, and if they think that this could have some benefits. So if building an interaction rather than interact with a just machine-like robot can somehow make benefits. And also was curious to know which kind of feedback do you think the robot should give to the co-workers to alert them about, I don't know, for example, the cognitive load or something like this?
Okay, let's say that as regard the aspect of the robot, I would say that it really depends on the scenario where you want to employ the robot. Since so far in my lab we have considered the industrial scenario, so the robot as a tool for the workers, I think that this thing of give some human aspect to the robot is not necessary, because we don't need the worker to have empathy with the robot. We just need them to have a tool that support them and help them physically. So I don't think this is an aspect that need to be considered. But for example, if you're using a robot in the healthcare, so as an assistant for the patient in an hospital, or for the all people in their daily lives, maybe it's something that you need to consider, because it's not maybe a tool, as I was saying before, but it's more like an assistant, a kind of assistant.
Referring exactly to your specific context of application.
Yeah, so it really depends on the scenario where you want to employ the robot. As regard the feedback, I was not mentioning it, but as I showed you before, we have this interface that is basically a screen on which you can see the model of the human with these color-coded spheres to denote the physical load. But we also developed some device, in particular a vibrotactile device that is basically a small device that you can put close to the joint of the human, and is able to vibrate in order to convey which is the physical load. So basically, the higher is the vibration, the higher is the physical load. So if you provide the worker with this kind of feedback, whenever they are using some improper body posture, or they are working with an excessive overloading, this device is able to vibrate and to communicate them that they are doing something that is risky for their health. So this, for example, was an idea. Now we want to go on in this direction and develop, for example, not only the alert of the risk level, but also to convey to the worker which is the direction. For example, they have to go through in order to reduce the physical load. So so far we developed this device to say, okay, this is an improper body posture, you need to change it. Now we are working on say, okay, this is an improper body posture, you have to move in this direction in order to make it more ergonomic. So this is the idea.
Okay, thank you, Marta, for your answer.
Cool. Yeah, I think that's maybe a really interesting discussion point for later. To what extent is the robot a tool, and what is required for collaboration? And just as a concluding remark, from my perspective, this was really interesting because I'm a psychologist, and what I look at is like how people see the robot and what it takes for people to collaborate with the robot and how it compares to collaborating with humans. So I think it was Enrico that said like humans are not predictable, especially from the engineering perspective, but somehow we humans are very good at predicting what others do. And I think that's a bridge and a challenge for all of the groups here. Before the organizers start pestering me, I suggest we start a 10-minute break now and come back to the second session in about 10 minutes after getting a quick coffee, some fresh air, and nature break. Do any of the organizers want to add anything?
I think we pretty much set, so I think we can take this break and then continue with the next session.
Cool. Thanks again to the speakers here, Marta, Maria, and
other
Enrico.
answers that we had no time to get through on the Padlet. Please feel free to answer directly on that platform.
Otherwise, we will come back to those points during the general discussion, yes, for sure. Thank you very much to everybody.
Thanks to the speakers, and we will reconvene.
And to Jessica, and we can reunite here at 3:10. Enjoy a very quick break and see you soon. Okay, so if we are ready, I would say we can start with the second block. If anyone from the organizers has introductory words or our second moderator.
Yes. So since we managed to be on time, incredibly, we can start with the second part. So the first speakers will be Dalila and Noemi, if you're ready.
Yes. Hi, Fabio.
Hi.
I am Anne. So I'm going to share my screen. Can you see it? I hope so.
Yes.
Okay. So, hi everyone. Thanks to the organizer for inviting us. And today I'm going to talk about our study, intersecting intention encoding and readout in autism. That is the result of the joint effort of different research groups. So first of all, when we think about autism spectrum disorders, we usually think about three main areas where the symptoms fall in. So we think about impairment in social interaction, impairment in communication, and stereotyped and restricted interests. However, studies suggest that there is also an atypical movement among the population of ASD. And most interesting for our study, there is also difficulties in predicting others' action. So our question was, why? Which are the mechanisms underlying these difficulties? One option is that there is difficulties in mapping kinematic variations to intention choices. So basically, regardless of the agent performing the action. Another hypothesis is that these difficulties are due to the different kinematic patterns of ASD and TD movements. So it depends on the agent performing the action. And this hypothesis leads us to think that there is a different impairment in recognizing actions according to who is the observer and who is the agent. So how did we try to answer to this question? First of all, we had an execution part. So what did we do? We asked ASD and TD participants, children specifically, to perform some movements. In particular, we asked them to reach the grasp towards a bottle, either with the intention to pour some water from it or to place it in a container. And we recorded either the videos and kinematic data with optoelectronic motion capture technology, as you can see in the on the hands here. So what did we do then? We selected 100 videos based on 15 kinematic features, for example, the wrist height on the bottle and the grip aperture. And we ended up with 50 videos per intention, either to pour or to place, and 50 videos per agent group, so ASD or TD. So later we had the observation part. So basically we showed these videos to ASD and TD children, and here I have an example. Okay, so this is in loop, but we just showed it once. And we asked them which was the intention that the actor was pursuing. So we had this 2x2 design. So we either had TD or ASD observer, agent, and TD or ASD observer. So we collected data from 35 ASD and 35 TD children, and these two samples were matched for age and IQ. And let's look at the results at the group level. So as we can see in the graph here, TD observers were actually able to distinguish the two intentions. So they performed above chance level, but there wasn't any significant difference between the agent in the video.
while the ASD observers were not really able to understand the intention, so they performed at chance level. And of course, there was a significant difference between the two groups. But then we also wondered, okay, let's look more in depth in the mechanisms undergoing. So our following question was, what's happening at the subject level and at the single trial level? And now I'm leaving the stage to Noemi.
Okay, thanks, Dalila. I'm trying to share my screen. Can you see it?
Yes, perfect.
Okay, so yeah, as Dalila said, I took care of the of some additional computational analysis, mainly to understand what was the relationship, the trial-to-trial relationship between the kinematics of the movements and the intention, both during the execution and the observation part. So for what concerns the execution, we trained this really simple variant, recurrent variant of a logistic model to predict intention from the movement kinematics. So the first question was whether intention information was actually available in the kinematics, and the answer was yes, since the cross-validated accuracy of both encoding models on TD and ASD actions were above 90%. So second, we wanted to know whether intention was encoded differently in TD and ASD actions. So here on the bottom right, I'm plotting the coefficients that the model assigned to each of the 15 kinematic variables that we take into account. So here the dark bars denote those coefficients that were significantly non-zero. So basically the intention informative features for TD or ASD actions. So the two patterns were not completely the same, but they had something in common. For instance, the height of the wrist was well separated between the two intentions, and this is the one marked in pink, for both TD actions and ASD actions. But in general, in ASD actions, the intention information was encoded within a more varied set of features, let's say. For instance, the grip aperture was informative, so it carried information about intention in ASD action, but not in TD actions. So they were partly overlapping, but not completely the same. Then we use the same kind of model to predict the choice, so the intention choice made by the children during the observation part from the visual kinematics of the movements. So as expected for TD children, their answers actually depended on the kinematics. So they used the kinematic information to give their answers. And these are the orange bars here. But we also found a weaker but still significant relationship between the kinematics of the movements and the answers given by the ASD children. So even though they could not discriminate between the two intentions, ASD children as a group actually gave their answers based on variations in the kinematics of the movement that they observed. So at the individual level, we labeled as readers those observers that actually used the kinematics. And then we further classified the readers into different groups based on how they did the task in terms of task performance. So for instance, we call the good readers those that not only could see the kinematic variations, but also used this kinematic information to correctly interpret intention. And these are marked in yellow here in the plots. But we also had several subjects that used the kinematics in a way that was completely unrelated to intention. So they did a different classification, and even some that inverted the classification. So they switched the two intentions. Now, interestingly, in the TD group, we had a proportion of good readers that was significantly higher on TD actions as compared to ASD actions. So this suggests some kind of modulation by observed action that was not observed in the group level task performance. So finally, we compared the weight pattern of the encoding and of the readout. So here I'm plotting the average distribution of readout weights for each group and condition. The dark bars, again, are the ones defined by the encoding. So they denote the intention informative features in the movement, which means that more readout weight on dark bars corresponds to a greater overlap between the intention encoding and the intention readout of the subjects. So we focus on two indices of intersection between encoding and readout. So first, we have the overlap index that quantified the overlap between the encoding and the readout, measuring the ability to identify which features were informative about intention. Whereas the second index quantified the alignment between encoding and readout, measuring the ability to extract the correct intention information from the features that were selected by the subject. So consistently with task performance, the alignment was significant for TD observers in orange, but not for ASD observers who couldn't do the task. But on the other hand, we found a significant overlap of TD encoding with TD readout and ASD readout with ASD encoding. So basically, both groups found it easier to spot the relevant features when the movements were more similar to their own kinematic pattern. So to conclude, even though autistic children could not discriminate between the two intentions, our single trial analysis revealed that they were not completely blind to kinematics. And what's more, autistic children could actually identify which features were informative about intentions in ASD movements, but then they could not weight them correctly in terms of intention. So both the general impairment hypothesis and the kinematic dissimilarities hypothesis that Dalila introduced at the beginning were from some perspective present, but at different levels. So that was all. Thanks a lot to the organizers for inviting us and to anyone who's listening.
Okay, thank you girls for the talk. We'll take time for questions later. And let's move on to the next talk. That's by Davide. Davide.
Here I am.
Eccolo.
Okay. I'm sharing the screen. Share. Here we go. Okay. Hi, everybody. I am Davide Esposito, and I am a member of the UVIP group, the Unit for Visually Impaired People, which is led by Monica Gori. And we're a group made of half psychologists and half engineers, more or less. And we try to pursue the following approach when we study a topic. We try to start from the scientific evidence. From this, we build technology that can be then used to answer scientific questions arisen before. But then we also use that technology to create training and rehabilitation procedures that in turn produce new scientific evidence. So we try to go in this with a virtuous loop to advance knowledge. Each member of the team has their own topic, more or less, and mine is about sensory motor contribution to body and space representation, and that's what I'm talking to you today. In particular, I'm focusing on the auditory spatial representation. This is interesting in terms of the visually impaired people, because space calibration, the calibration of the space representation of sounds happens through vision in the early stages of life. So what happens when vision is lost early in life? It is not completely clear how, but it seems that the audiomotor cues compensate for the vision loss. But there is a problem, and the problem is that the loss of vision early in life induces a delay also in the motor development. So these people, these children, are relying on cues that are affected themselves. So in the last years, there have been attempts to develop audiomotor trainings to foster the calibration of the auditory space in this particular population. And data is successful, actually. The results are positive. Yet there is an issue with lab-based trainings, and the issue is that they tend to be focused on a specific skill, and they are limited in time by their very nature, and their long-term effect is unknown. But there is a kind of audiomotor trainings that is already available and then doesn't have all these limitations. And that is the sport, basically the adapted physical activity for the visually impaired people. So our question is, do early blind individuals which have high expertise in a sport practice have a more mature space representation, egocentric space representation? To answer this question, we focused on a specific sport, the five-a-side football or the blind football. That is an adapted version of the classic football, where we have the ball that emits a sound. Also, the opponents must signal themselves with the voice, and also the goal is acoustically signaled by the person that is behind it and uses the voice. So it's a very rich auditory environment in which the players move. To try and answer the question about the degree of auditory space representation maturation, we try to use a different approach that comes from the intuition that if we have a different relationship between bodily information and spatial information, and we create an interference and we alter the relationship between body and space, then maybe different body and space configurations react differently to this alteration. In particular, we focused on an alteration of the trunk on the head audiomotor contingency, that is the relationship between movement of the head and consequent change of perceptual information. We did it by means of virtual reality, auditory virtual reality, and inertial body tracking. And we created a virtual reality platform. I hope you can hear this. So we have the arrow that is driven by the rotation of head and trunk, a combination of rotations. In particular, we defined 4 experimental conditions that come from 2 factors. The first factor is the contingency, that again is the cause-effect relationship between movement and change of perception. In the contingency factor, we have 2 levels that are the preserved level, in which the arrow direction is driven by the head rotation and the trunk doesn't have any impact. And we also have the altered contingency level, where the arrow direction is given by the trunk rotation. And also the trunk rotation creates the interference where the virtual ears orientation is given by a summation of head and trunk. So that, for example, if you are still with the head and do like this, your auditory scene turns. We also have another factor that is the direction factor, which defines the relationship between body and space. In the central level, we have head and trunk that start misaligned, and the target is placed straight ahead in the virtual environment. In the lateral condition, we have head and trunk aligned, and the target is on the right or on the left. So a misalignment is required. We tested a group of 10 congenital blind individuals and a group of 11 sighted individuals with the idea that if there is a difference in audio spatial representation maturation, and this platform is able to capture this difference, then some measures should be again different. And the measures we focused on were 2 that investigated spatial performance, that were the accuracy in hitting the target and the precision, again, in hitting the target. We also try to assess the kinematic behavior of participants with the root mean square of the head angular jerk and of the trunk angular jerk, with the idea to capture the amount of movement of these two body parts. So we went with an univariate analysis first, just non-parametric univariate analysis. And indeed, we found in 7 out of 16 comparisons, a significant difference where the early blind individuals actually had a worse performance, so less precision, less accuracy, and much and more motion of the corresponding body part. So we decided to use this method to investigate our initial question. So can extensive audiomotor experience from sport calibrate and foster the maturation of the auditory spatial representation, egocentric representation? So we used the exact same methodology. And we also tested visually experienced, we labeled it in this way, so visually experienced early blind individual that had no extensive audiomotor experience, but who lost vision a little bit later in life, in the late stage of the expected spatial calibration from vision. We went with first a univariate analysis, classical single case univariate analysis. And we found the early blind football player to have an intermediate behavior that nevertheless was slightly going towards the one of congenital blind individuals. Indeed, among the comparisons, the test we did, only one was significant for the comparison between the player and the sighted individuals for the trunk movement in the, let's say, in the lateral condition. But this is univariate, so in this way we cannot capture the overall behavior of an individual. We miss the relationship between the variables. So we tried to borrow a machine learning algorithm to classify the player. So we decided to go with a linear kernel support vector machine. We trained this model on the participants from the first experiment, so the 10 congenital blind individual and the 11 sighted individuals. We assessed the training model performance by means of leave one out cross validation, and we picked the support vector machine parameter, hyperparameter C value, in order to maximize the sensitivity to the early blind group, to the early blind class. Our model reached a sensitivity of 100% on the training set, and actually also a very high accuracy. Indeed, we had all of the training congenital blind individuals that were correctly classified, and only one sighted individual that was misclassified as early blind individual. With this model, we tested the early blind football player, and the player was classified as a sighted. Instead, the early blind visually experienced participant was classified as congenital blind and early blind. So from this, we concluded that audiomotor experience actually can calibrate the egocentric auditory spatial representation. Yet, it seems that the motor behavior and the motor strategy that people use develops and depends strongly according to the availability of visual information in the early stages of life. And that's all, and thanks for listening. If you have any questions, I'm happy to answer them.
Okay, thank you, Davide, even though you went a bit off, but it's okay. Let's go with the next one. That is Marco, if he's ready.
Yes, good morning, everyone. Hope that you can hear me well. Okay. Here we are. So I'm Marco Emanuele. I'm a PhD student here at the Center for Translational Neurophysiology in Ferrara. And today I will talk about this work that we have recently published, in which we focused on the organization of motor synergies in preschoolers with autism. So as Dalila has already remembered before, autism is a neurodevelopmental condition.
Marco, do you want to share the slides, maybe?
Sorry, you cannot see my screen?
No, we just see your face.
Sorry. Okay, sorry. And now, okay. Can you see the slide now?
Yes, now it's good.
Okay, sorry about that. Okay.
No problem.
So as I was saying, yes, this was the first slide, the title slide with the title of the work. Autism involves problems in these three domains: social and communicative impairments and repetitive behaviors. These are conditions with a strong genetic background, and these problems are often paralleled by intellectual disability of variable degree. So on top of these problems, there are motor impairments. Children with autism move differently from neurotypical children, and for example, they have difficulties in anticipatory planning, which means modeling in advance the parameters for their goal-directed actions. And this is particularly evident when they perform motor chains, such as picking up some food and bringing it to the mouth. These kind of movements are more fragmented, temporarily fragmented in children with autism compared to typically developing children. Additional problems are difficulties in using sensory information for adjusting unfolding movements, increased variability in motor execution, and also increased inter-subject variability, which means that movements in children with autism are, let's say, more idiosyncratic. One topic that has received little attention so far in literature dealing with motor problems in autism is how these children cope with a redundant motor system. The human motor system is in fact highly redundant, which means that, for example, this little guy here can reach his toy through many different and goal equivalent trajectories. And each of these trajectories can be actually achieved with many different patterns of muscle activation and joint rotation. So this redundancy entails ambiguity when one single set of motor commands must be selected and associated with a behavioral goal. And this ambiguity is solved by the motor system through the motor synergy mechanism. That means by co-controlling multiple degrees of freedom at once, which reduces the number of variables that must be tuned at the same time, and reduces the computational burden for the motor system. Of course, different synergies can be scaled and combined with each other to produce widely differentiated and flexible motor behaviors. So we asked whether this mechanism is intact or not in children with autism, and how this may impact the typical development in autism. So we designed a quite simple ecological and self-explanatory task in which children are just to reach and grasp a felt tip pen and complete a drawing in front of them. For example, here they had to draw the eyes of this smiling star. We were in particular interested in reaching kinematics and hand transport kinematics that we collected with optoelectronic system. Participants were mainly children of preschool age, kindergarten age. So first of all, it turned out that children with autism moved faster than neurotypical children, and with a more ballistic movement, let's say, with a more symmetrical bell-shaped velocity profile, with a lesser time, lesser deceleration time. And additionally, movements in children with autism were more variable in terms of trajectory length, in terms of path. So this first result just confirmed that children with autism are less capable of selecting consistent motor parameters and producing stable and let's say consistent motor representations. In addition, when we applied principal components analysis to 9 degrees of freedom of the upper limb, we found that the cumulative variance accounted for by the first 3 principal components was lower, significantly lower in children with autism, showing that interjoint coupling was, interjoint coordination was weaker in this group. So each joint was controlled in a more independent way, less coordinated way. And interestingly, this finding was correlated with the ADO score, which is a gold standard assessment tool that evaluates several social communicative skills in children with autism. And this latter finding made us speculate that the ability of exploiting the motor synergy mechanism for motor control may somehow impact the development of more complex socio-communicative, socio-cognitive skills. So somehow drive atypical development in autism. And actually, previous work has shown that synergies are not only an effective mechanism to control self-produced motor behavior, but also a noise-resistant system for coding action observed in other individuals. So the impairment of motor synergies may influence the development of some basic form of social interactions such as action observation and action coding, and therefore influence the development of social and communicative skills. The second goal of our work was a more translational one. We asked whether kinematic features, motor features were good early diagnostic predictors for autism. As I said, our sample involved young children, kindergarten age children. So we trained a support vector machine to perform automatic classification of autistic versus typical developing children based on 17 kinematic features, and we got a fairly good single trial accuracy of 0.74. Then we used the percentage of positive responses that the supervector machine provided in each participant over 40 trials to build a receiving operating characteristic curve, which had an area under curve of 0.9095, and with a good specificity and sensitivity. An important point for translational application is that we got a quite good result, an accurate ROC curve, also when we randomly selected only a subset of trials in each participant. So with just 6-7 trials, we got an ROC curve of over 90% accuracy. This is important in the field of autism because autistic children are often poorly compliant. So translational applications need brief procedures that are effective with a small number of trials. So in conclusion, we show that children in that the organization of motor synergies is impaired in children with autism, and these characteristic may influence the development of social cognitive skills and somehow drive a typical development in autism. And in line with also in line with previous work, we show that motor signatures are effective biomarkers for diagnostic purposes in young children with autism. So that's it, and thank you for your attention.
Okay, thank you very much, Marco, and also the other speakers for your super interesting talks. And now it's time for questions and discussion. So there are already many questions, but as you may have noticed that I'm not as nice as Cisco, so I will override them and I will start with one of my questions. And this question is to all the speakers actually, so who want to answer or who have an answer. So since I'm more roboticist, sort of halfway between the previous talks and this talk. And this is an iCog event, so for a cognitive architecture for, let's say, robotics, more or less. I wanted to ask all the speakers how their, let's say, work, how they think their work on impairments, ASD conditions could improve, could help in the development of cognitive architecture for robotics or robotics more in general.
Who wants to start? So maybe I can give a first answer. I mean, characterizing motor impairments in autism and the possible influence on typical development in this condition may help producing diagnostic, but also maybe rehabilitative technologies for improving motor behavior in children with autism, assuming that improving motor behaviors might influence also the general clinical outcome in children with autism. So.
Okay, I see. Some other wants to try.
Yes, I would like to connect to Marco's answer. So, for example, when focusing on observation, this kind of study help us to understand how we read intention from others. So in this case, we can actually see what's the focus of our understanding when observing others. So I think that this can help improving what are the specific features that have to be, like, for example, enhanced when interacting with a robot on one hand. And on the other hand, I think that for the execution, for example, as Marco was suggesting also, there could be like a double-fold help from iCog and to iCog. So for example, a good option would be using an iCog, for example, for rehabilitation purposes, and for example, for training an ASD-like movement towards TV-like movement, for example, and this would combine both the observation and execution part, for example, of our study.
Okay, thanks, Dalila. So, any other idea?
I can try with mine if you want. Well, mine was more in the sense of let's say calibration of movement in space and understanding space. And in terms of cognitive robotics, it may be interesting to see how humans do it, to have insight on how to create the replication in robotics. I mean, I know it is already kind of like this. There are attempts to do so, yet I think the main focus so far is on the understanding of movement with respect to vision. This may be interesting to see how to do something, how to approach to an issue, for example, in situations where vision is unavailable or stuff like this. I mean, robotics can be adapted to different environments and situations, and each sensory channel gives its best in different environments. So vision is the richest one in terms of spatial information, but it is not the only one. And so also being able to adapt to also the differences in sensory information, in the available sensory information by using motor exploration or something like this, to understand how something that is undeterministic but more likely probabilistic can be understood is can be it can be some help, at least to inspire.
Yes, if I can add something, I think well, what David has shown is also shows very well the importance of, well, this is probably what he said, I'm just rephrasing in different words, but the multimodal integration, you know, the fact that sensors, sensing channels are not separated, and they are, you know, purposely mixed, and they are mixed very often through movements. So the fact that the body moves actively, it is used with the specific purpose of improving sensory feedback from the environment. So and these examples, so with blind people showing, which shows that the lack of vision is affecting, you know, the representation of sound is not so trivial if you don't take into consideration that there is an intimate relationship between these two sensing channels, and that this link is built through movement. So this, I think, it is, you know, the foundation of embodiment, you know, this kind of studies. And of course, also I see the others also from the study of the kinematics of children with ASD, and the difference with humans, with typically developing children is also very interesting. If I can ask a question there, I mean, why is there this difference? I mean, you have described very nice experiments where you showed that there are differences in perception, in movement, you know, in understanding intention, goals, and so on and so forth. But do you have an explanation of, you know, why a problem which is usually linked to social interaction, in fact, as you know, shows a difference in motor behavior somehow?
I would answer like that. Probably motor problems influence social cognition in a kind of bottom-up way. So basic alterations of motor interaction with the external world afford us and with other people, of course, may influence the hierarchical build up of more complex abilities, including social abilities. As I mentioned before, motor synergies, for example, are not only useful for coding our motor behavior, but also for coding others' motor behavior, that we observe in our everyday life. So problems in self motor representation in turn may influence our ability to interact with the external world and with other people. So probably the answer is like the reverse question: how alterations in motor kinematics influence and impact the development of social cognition.
And also social interaction is a lot about decoding the intentions of the person we are talking with. So, or the person that is performing an action, and that is a lot related to kinematics. That's why our study was about intention specifically, because it has a lot to do with social interaction.
Okay, so thanks, guys. There's still some minutes for some questions from Padlet, maybe. The ones we can't answer, I would ask you if you have time to answer yourself, maybe on later. But let's start with one for Dalila and Noemi. L'ultimo. Okay, there's one by Anonymous. How can the findings from your study on ASD and TD intention reading abilities be used to model a cognitive functionality for intention reading? Could also the ASD results be useful and taken into consideration for a more inclusive approach?
Well, that's a hard question. No, I mean, I also read the previous question before, so I tried to answer to both, actually. I suggested from that question, I mean, when we talk about ASD, we should talk about ASDs. So autism spectrum disorders, since there is a really heterogeneous framework. And in order to understand exactly what's going on, I think that it would be interesting to take into account also other measures, and like spanning from genetics to functional imaging to behavior. So it's really hard to have a detailed frame of exactly what's going on, but I think that a more like inclusive approach would be like interesting to be able to answer to that question, if I got it correctly.
Yeah, I'm not very sure I got exactly what the question meant, whether it was related to intention decoding specifically, or to a more robotic point of view, or if the person who wrote the question can clarify it, I would appreciate it. No?
Okay, well, maybe, I don't know if the author of the question can clarify also in the Padlet. Noemi and Ayla can give more specific answer later. And
sure. The question is not very clear. I agree, but it was not me that made the question. I was just supporting the fact that the question is not very clear. But all questions are good, so I'm sure there is something good in the question. We have just to
Yeah, there was.
That's why I was asking, because
Yeah.
I'm sure it has something useful in it. I was just wondering whether it was about like some more inclusive in the sense of taking also into account the kinematic variability related to intention that we have in autistic individuals, and not only like taking into account the typical pattern of typical individuals. But I'm not sure I got the question, so I was just asking. Well, anyway, we can go on
Okay.
in the
Let's go with
platform thing.
one for Davide, maybe. Some particularities of your model be useful to be applied in cognitive robotics for developing a perceptual framework? Davide?
Well, I think this more or less aligns with the answer, with the question, with your question. So
I'll agree with your analysis. I would say that we can move on from one last question for Marco. Which one I like more? Okay. You said the impairment of the motor synergies of the ASD children correlated with the severity of their autism. Can you please tell us why, which tests was the severity of ASD measure?
Sorry, why?
Can you tell us with which tests was
with which? Okay, yeah. Oh, it was the ADOS score, which is a standardized assessment tool, gold standard actually for assessing autism, which measures social and communicative skills. It's kind of a clinical scale, so that was.
I think this answers the question.
Yeah.
So that's all for this session, I would say. Thank to everyone who gave their, let's say, contribution. But don't leave, please, because now it comes to the most interesting part. That's the final discussion. And I would say that if the organizers want to take the stage, I'm done. Okay. From the directors, I hear that we have a 10 minutes break to organize a bit the things. So see you back at 4:15.
Yeah, 4:15 is good. So.
Okay.
Thank you.
See you back for the open discussion.
In a while. Thank you.
Hello everyone, welcome back to the last part of our workshop. It will be an open discussion. Before starting, I would like also to ask the people from the robotics field, because we have only asked from people from the cognitive neuroscience. I would like to ask the other people how they think that they will be, they can benefit from the methods in cognitive neuroscience, or also collaboration with psychologists in order to build cognitive architectures to the robots.
So, Kyveli, this is addressed.
You don't hear me? No, because we are pretty.
Okay, I was asking Kyveli, is this addressed to the members of the robotics group? So should I like spotlight Maria, Marta, and Enrico?
No, maybe we can ask it no?
Because we cannot hear them.
Okay, maybe I'll introduce a bit the topic and then you can ask the question, no?
No, not the question.
Oh, sure.
Sorry, can you repeat the question, Kyveli, because I'm not sure I've understood.
Okay, so can you hear us?
Yes.
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 Sorry, there are technical problems. Can you hear us, right?
Yes.
Okay.
Yes.
It was us that we were not able to hear you. So, okay, so anyone who wants to answer the question of Kyveli?
I think we asked for the question to be repeated.
Yeah.
Okay, so Kyveli can repeat it.
Yeah, if you can repeat the question.
Do you hear me now?
Yes.
Okay. Yeah, I asked the people from the robotics field, how do they think they would benefit from using methods of cognitive neuroscience or collaborating with psychologists in order to boost the research in cognitive architectures for the robots?
Okay. So thank you for the question. If I can start. I mean, for what concerns my research, I think that it would be very useful to work with psychologists in order to make the people, I mean, in my case, the worker, but I guess also the patient of an hospital or the people in their daily life, to serve the robot, to basically to understand how we can improve the robot algorithm, the robot behavior in general, in order to make the people accept the presence of the robot in their environment. Because I mean, we are developing a method to assist them, to guide them, and so on. But the main issue would be, a big issue would be if this person don't want the robot to help them. So it would be very interesting to understand what we can do in order to make the robot more acceptable for the workers, but also for the patient and the people in general. So maybe I would start, for example, to do some questionnaire maybe to the people to ask them how they expect the robot to behave, what they expect from the robot, which are the characteristics of the robot that they would like to have, and starting from the answer to this questionnaire to understand what we can do in order to improve our framework in that sense.
Yeah, from my side, if I can go on, I think accessibility is very, very important, is a key point, because not only for the robots, because if you think about medical environment, of course, there are people that are patient, that they are ill, they have trouble, so the acceptability of the robot helping them is a key part. But also from our side for the wearables, because we have to wear technology, and it's not always easy to ask people to wear the technology because they are scared of wireless communication, they are scared of get injured for any reason, and then it should be also the wearability is very important, and the psychologist for this I think could be very, very important for us. Yeah, I think this is mainly what we can do in this, let's say, for a collaboration with psychologists. But I think another point of collaboration very important for us could be to understand better what we can add to our technology in terms of different sensors, different, let's say, way to collect information from the body that is, say, useful for our activities. Because for the time being, for instance, we have this system that belongs to us, so we can add whatever we want. We can work on it, we can improve it, and then we can add, we can synchronize different systems, different data collection, sensors, and to add it to the body. And for that, we need to expand a little bit the technology and our knowledge in terms of robotics to different fields that are very similar to what I heard today.
My turn, I think. Basically, my effort here, basically, I hope in a collaboration, because my effort is that the psychology world should understand basically and use iCog as an active presence, because by my understanding of the work that is carried out in Erselli, basically iCog is used as a predefined sequence of command a priori the human-robot interaction. So basically, I feel quite useless because in my group we develop a lot of algorithm for object detection, for gaze estimation, for several tasks, and then iCog in a real experimental scenario that is the missing part of our group is not used as active presence, but just as a passive robot there. Only, I don't know, but is very, very passive from our side without any intelligence. So I think that combine the intelligence of that basically a limited intelligence that we have on iCog with your experimental settings, I think that could be your potential and challenging.
Thank you very much for your answers.
Okay, so
but also the opposite, because there's some dead air, so don't know if I'm allowed to ask a question, but what I noticed that we talked about interaction, and what I noticed with robots is that that interaction or any sort of action or detection is always based on an algorithm, and there's a specific decision in time. So for example, Maria's work, and not to single you out, but I think it's quite a good example of knowing that eye contact is established. There's a decision, and iCog acts on okay, there's a prediction that eye contact is established now. We as humans, it just kind of is, and not only that. So there's the decision latency. It's also we kind of instinctively know, most people, when to make eye contact and when not to, and we don't think about it on a conscious level. So what I see as a researcher often is that it's not just a latency, it's like a different mechanism at play. And I'm just wondering out loud, is there anything the roboticist could do to make that kind of interaction more natural and intuitive? So maybe another question to the roboticist speakers.
Could you clarify a bit, Cesco, sorry, the question?
So how could we bridge the gap between, okay, a robotic system can detect a certain type of